First of all, to introduce myself, I'm Jose Luis Hidalgo. I am VP of Analytics and Data Science in a company called Nextail Labs. In Nextail, what we do is we apply machine learning techniques to optimize the inventory cycle of retailers. So those are our clients. This is the kind of things we do. By the way, we are hiring, and we're also always looking for clients and looking for finance. So anything, come to talk to me. This talk is about whether we are ready to apply Bayesian inference to big data. And first of all, I would like to clarify a few concepts because I mean, both Bayesian, inference, and big data, I mean, three of them are overused terms that might mean different things for different people. So I'm going to start with maybe the hardest one, which is Bayesian. What do we mean by Bayesian when we talk about Bayesian inference? Do we mean that we apply Bayes rules? Well, Bayes rule is math. We do math, we do correct math, whether, I mean, this is not up to anyone. You're not Bayesian because you apply Bayesian rule, just like you're not multiplicative because you apply a multiplication rule. There is this old, I don't know, confrontation or this old thing between Bayesian statistics and frequentist statistics. And this is actually, I think, a bit of an old story, and I think we are pretty much past it. And actually, I was a bit surprised when I first heard that the one that created the Bayesian term to talk about Bayesian probabilities and Bayesian models was actually Fisher, which is well, pretty much considered the father of modern statistics. I mean, he's the one that put some mathematical rigor to statistics and developed frequentist statistics, the kind of frequentist statistics that then we've been doing mostly during the 20th century. So Fisher called Bayesian, I mean, when he invented the term, actually what he was talking about what I mean, he called reverse probability. And I think this is a very good concept. This is a good frame to understand. Basically, probability in his views, in his mind, was associating some causes to some effects. So you have, I don't know, two black balls and one white ball in a basket, and you take one, and 2 out of 3 times you take out the black one. So you associate some known causes to what are going to be the effects, what is going to be the outcome. Now, reverse probability, and the discussion was whether that makes sense or not, is doing the opposite thing. Is I know what the outcome is, and I want to know what caused that action. And basically, to work with reverse probabilities, to manage that concept, to be able to model what's happening based on the outcomes, you need Bayesian, you apply Bayesian rule, you need Bayesian statistics. This is what Bayesian statistics is about, is getting the data and figuring out how it was created, figuring out what happened that made that result in a probabilistic way. Let's say in a process or in a that is probabilistic. And in that regard, I don't think we can talk anymore. I mean, most people don't do anymore talk about Bayesian statistics, but we can definitely talk about Bayesian models. I think that's the interesting thing here. Bayesian models is the models that we make where we try to infer the causes, or now we will call them the parameters, based on the data. This is the kind of models we're going to be talking about. Another term that is much overused and might be confusing is inference. People in classical statistics, they talk about descriptive statistics and inferential statistics. And in there, inference means something like, well, getting to some conclusion, like A/B testing or whatever. I mean, this is what they call inference. This is not what we're going to be talking here. In machine learning, it's also quite typical to talk about the training and the inference phases. You train the model, and then you use the model to infer some other case. This is also not what we're going to be talking about here. The term inference, what we're going to mean by it, what we're going to mean by inference is the deduction of those parameters in the model that created that outcome. So I have a probabilistic model that depends on many parameters, and I have some real-world data that I think, I believe that came from a process that is modeled by that model. Inference means taking that data and figuring out what are those parameters in that model. This is basically what inference means. And once I do that, I can use that model to predict the future, to make, compare to other models, make validate hypotheses, whatever it is. And the other one, the other concept to clarify here is big data. And well, I think there are many, as many definitions of big data as vendors trying to sell something. So what I'm going to be talking about here is the fact that over the last decade or the last few years, we are able, and we are actually doing it, we're able to extract information that is hidden in much larger volumes of data than we used to. It's not about that we manage billions of records. We did manage billions of records in the 90s and in the 80s, and we had the banking transaction systems. It's that we use billions of records to figure out one person preferences in movies. That's the big data sense in my view. I mean, or at least when we're talking about analytics. So we're going to be using massive amounts of data to figure out something, well, of a small scale. It's not like a one-to-one relationship between what we have and what we infer. It's a huge number to a small inference. As I said, this talk is about whether we are there. We can use Bayesian inference. We can use this kind of tools with big data. And I think a little bit of history might clarify what we're talking about. I think we can start with early Bayesian models. This used to be quite an academic field. This used to happen at universities rather than at companies, where they could, they made some mathematical model, which was a Bayesian model, and they had, well, some analytical tools, basically. So basically, you would just try to figure out the integrals and figure out the maths, so you could reverse your model and do the inference. But you can only do that to very simple models. But just doing that, you can get to quite interesting results. I mean, you can get, for instance, to things like Gaussian processes, or you can get to latent Dirichlet models. Some of those models, they are tractable with analytical tools, and then you can do the math, and then you end up with the way to solve them. But most of the models, most of the realistic models, and most of the models we are interested on, well, they have very strange distributions, they have very complex relationships between variables and so on, and they are not tractable analytically. So we need some kind of simulation or numerical methods or whatnot. In the 90s, even if, the concept came up earlier, but in the 90s it became quite popular, what's called the Markov chains Monte Carlo methods, the MCMC. Markov chain Monte Carlo methods is basically a way where you can have one of these models and you can create a process, a Markov chain process actually, that gives you samples of your posteriors, of the things you are interested on. So you can sample your posteriors, basically. You can get an experimental distribution of what your posterior is going to look like. The good thing about this is that this is, or the interesting thing about this is that this was a generic mechanism that allows you, for all these kind of models, to, well, do inference, which is what we're trying to do, to predict the posteriors. The problem with it is that it was extremely expensive from a computational point of view. Let's just think that what in other kinds of models would be one variable, in probabilistic models is a whole distribution. And to have a good idea about a distribution, you want to sample it, I don't know, at least a few thousand times. So just because of that, you're multiplying by 1,000 times your complexity for each single variable that you're managing. So things become intractable very quickly. And they're also quite finicky, these early MCMC models. You need to be very close to the solution for it to converge properly. You need to, I mean, it was quite tricky. But even so, using MCMC models, they did some quite interesting feats. And actually, MCMC models had a lot to do with the popularity of advanced statistics in sports. Sports, baseball specifically, which is very data rich, and you're having data sets that are probably in the hundreds or thousands of data points, like, I don't know, the average score of each player and whatnot. And you can do latent variables models, and you can, well, try to play with that, and it can give you some good probability distributions of what's going to be the outcome, and that can have some value in terms of bets, and that can have some value in terms of figuring out if a player is more valuable than its price, and all these kind of things. So in the, I think it was in the late 90s, early 80s, using MCMC and using probabilistic models, they did quite interesting advances in statistics applied to sports. I mean, and it was very popular in academic terms. I mean, you see a lot of papers from that time where they develop a very complex model, and at the end of the model they say, well, and then we do inference using MCMC, and the last few paragraphs is like how they did the inference, and then they come up with the results. And even in the 90s, there was people already playing with variational inference, which is a very different way to tackle the same problem, which is even harder, at least from a computational point of view, at that point in time. In the aughts, in the first decade of this century, a novelty came up or became popular. It's also a little bit older, which is probabilistic programming. Probabilistic programming is a way to tell a computer, to express to a computer, a probabilistic model. So I have my probabilistic models that says, well, this variable behaves in this way, and have these influences and these dependencies, and there is this model and so on. Well, with probabilistic programming, I can tell that to the computer directly. And then, because I have generic inference mechanisms, I can say, okay, this is my model. Now, please do the inference. Infer these and these parameters. And then these Bayesian inference systems started becoming popular, like JAX, like BAX, STAN, which is already quite popular, and so on. And also during this decade, well, there were some significant advances making the inference more powerful and easier to manage. So there were more and more models that we were able to make it converge. We were able to calculate something about that. And then in this decade, and actually in the very last few years, there's been some very significant advances. There's been advances in the theory, where we have new algorithms, we have new ways of attacking these problems. There's also been significant advances in the technology. We are now using GPUs, we're now using automatic differentiation, we're using the same technological advances that have made neural networks so powerful lately and so popular. Well, those same advances, I mean, even the same libraries, even TensorFlow and whatnot, we're using the same ones to speed up our models, our Bayesian models. And here, I think it's quite interesting to differentiate when it comes to getting larger and larger models between tall data sets and wide data sets. And what I mean by that is a tall data set is when you have a very large number of cases. So you have billions of data points of the same kind. So it's like a very long list of a huge sampling or of some process or something like that. And with tall data sets, which is basically the realm of neural networks require tall data sets because they learn very little from each data point, so they need huge training sets. With tall data sets, what you want in order to be able to manage larger and larger sets is to be able to split them, basically to parallelize and to split them in pieces. It was traditionally not possible. You needed the whole data set all together, so you couldn't just split in many machines. But some of those advances that came up this very decade, actually a few years ago, now allow us to do what's called mini-batch, which is basically training these models by batches, so we can parallelize. So basically that opens up the possibility of applying these models to tall data sets. Now, we were not able to apply things like this to data sets beyond 10 to the fourth or something like that. But now, because we can horizontally scale, well, we get a couple of levels of orders of magnitude more. So instead of 10 to the fourth, we now are at 10 to the sixth or whatever. So we scaled horizontally because of these technologies that allows us to tackle tall data sets. And the other thing, the other dimension why data is getting bigger and bigger is because we have wide data sets. Wide data sets means the data sets in which each data point has a huge number of dimensions. So let's say an image. And then, I don't know, when we have an image and it has 1 million pixels or whatever, well, we have 1 million features. And actually, when we use wide data sets in neural networks, we tend to try to make them less wide because we have problems with neural networks and wide data sets. But in here, the interesting thing is that running the model and running the inference are independent processes. So you might have an extremely complex model, but you might be doing the inference only for a few variables. You might be interested only on a few outcomes from that huge amount of data. And as long as your model can manage that huge amount of data, your inference process is not affected. So the only thing that happens with wider data sets is that each step of the process becomes more complex. So if I was able to manage images this size, now to be able to manage images this size, I'm just multiplying by 2, let's say, because the image has double the points. Whereas in a neural network, as I make the data set wider and wider, it grows complexity exponentially. So that's why the first thing you usually see in image recognition in neural networks is that you take the image and you scale down to 200 by 200 or whatever, because doing with the full scale is too hard, no? Well, in this case, we are linear, if you want, with the wideness, and we also have now technologies to spread in separate machines. And these two advances, these two things, means that we are now being able, at last, to make probabilistic models and apply them to huge data sets. I mean, to real well, relevant applications. I'm going to quickly go through a few applications from different fields. Very interesting applications are coming up in cognitive sciences. We're basically doing the exact opposite than that our colleagues from neural networks are doing. They're trying to use ideas from how the brain works and implement them in our artificial neural networks. There is people in cognitive science that is doing the same. They're just doing the opposite. They're trying to figure out how the brain works, and they're trying to model that, to model how the brain works, and so they can try to predict. So for instance, you can do experiments about memory. You model how memory works. For instance, there is some interesting models about how memory fades over time. And you make some model saying, okay, the amount of fading over time has a relationship with how related that piece of information is. And you provide people with different pieces of information. Some of them are related to something else. Some of them are isolated. And then you put some coefficients, and you model how the memories are going to fade. And then you do some experiments, and you're able to quantify how the memory fades, and you're able to validate that assumption that you made, that how fast the memory fade depends on how related to other things is. You validate that hypothesis. So this is the kind of things that people do in cognitive sciences with Bayesian models. And now they're being able to do this at much larger scales, and also with data sets that are not purely coming from experimentals, from experiments, but from real-world data sets, like, I don't know, preferences data sets and things like this. Another example from fintech, from financial technology. There is one thing in which financial models have traditionally been quite bad is in predicting unlikely events, like what happens in the tails, what happens when everything goes wrong. And the kind of models that you can treat analytically, and most of the models that people use tend to have a very bad behavior on the very exceptional cases. And there is this mathematical technology called copula models that allows you to, among other things, allows you to model how things work at the tails, basically what's called the correlation at the tails. And it's interesting to see that some things that are positively correlated at mid-values become negatively correlated at the tails, and the other way around. And by being able to model these kind of things, you can predict things like survivability on a crisis, or you can predict risk at the very large models and things like this. But these models used to be intractable mathematically, at least for large numbers of assets and so on. Now, thanks to this inference technology that we have now, I mean, at the end of the day, these are probabilistic models, so we can use these inference tools, even if they used to use different tools, but now they're starting to use this kind of inference tools to be able to run these copula models, and this allows, for instance, to predict market crashes and things like this. And not only that, it allows you to measure a market crash and have some model of how many people is going to survive. So for instance, they do survivability analysis using these kind of models. From artificial intelligence, another example, this one is from MIT. When you do image recognition, usually what you do is you train your model with a huge amount of images, and you hope the model will learn something that allows the model to recognize images of cats and dogs, or tell people apart, or whatever it is. Now, there is another way to do it, which is you might have the way to create images yourself, and then you want to compare the images you create with the images you get. So in this case, there is a case from MIT, quite interesting, in which they have a 3D model of a head, basically of a face, and it's driven by a series of parameters. And they also have some parameters about the lighting and the quality of the photo, whatnot. So basically, by tweaking those parameters, you can get different faces and in different situations. Then what they do is they compare, when they get a photo, well, they use Bayesian inference, they use these inference mechanisms to get the right parameters so that the photo looks as much as similar to the one they get. And using these, they can do, for instance, face recognition. They can know who that person is because they got the parameters for, well, the different features of the face. Now, they can do this with extremely, I mean, with a much smaller training set. I mean, they don't need millions of faces to start recognizing faces. They just need to have a generative process that is good enough to create faces that can be recognized. So this allows them to do image recognition at a fraction of the cost, particularly in terms of training data set. And another one, this is a bit closer to my own day-to-day. In business operations, we have what we call the inventory information problem. Basically, we know, and that's been certified, I mean, that's been investigated a lot. We know that at least 30% of the inventory information, or the information about inventories that you have, is wrong. So, I mean, inventory specifically is an extremely noisy data set. You really don't know what you have in your warehouse. You really don't know what you have in your shops. You only have, well, relatively an idea. But you can have a generative process that gives you that information. You know, well, from the movement from your warehouse and the units that you sell and the units that get lost and the units that are stolen and whatnot, you can create a process that gives you that information. And then you can put your information there and try to learn the process, and that will allow you to know which ones of those data points are more likely to be incorrect. And then it will, the system will learn that, and you will say, okay, this is my inventory information, and it will give it to you, well, you know, this, and this is probably wrong. So this has quite a lot of value in terms of, well, operational optimization. This is the kind of models that we do with I mean, using Bayesian inference mechanisms. And just a few conclusions. If you're a data science practitioner, well, familiarize yourself with these kind of models. I think they're becoming more and more relevant and more popular. Well, there is a few tips in there about technologies and libraries that you might be interested on. Edwards, in particular, is quite a new development. It's less than 2 years old. And among other things, Edwards allows us to do a probabilistic inference over TensorFlow, which means we can scale the models quite easily. If you're responsible for technical infrastructure, well, understand that your big compute needs are not only going to come from your neural networks, you're also going to have other types of models that are going to need big compute. We're going to need clusters, we're going to need Sparks, we're going to need distributed computing architectures to run these kind of models. And if you're responsible for business, the only thing I can say is ask for more. I mean, things that were not possible 2 or 3 years ago are possible today. And of course, things that are not possible today will be possible in 2 or 3 years. In this case, in the case of Bayesian inference, the last 2-3 years have seen a massive increase in the power of these techniques. So things that were not even feasible, I mean, things that people didn't dare to think they were possible just a few years ago, today there is someone else doing it. So ask for more. I mean, even if it seems, or even if in some cases people tend to think these methods are not applicable to your problem because your problem is too big, it might very well not be the case anymore. I think that's my my message regarding this. And thank you very much. And if there is any question, well, if there is any question, we can take them outside, because we're running this room with a little bit of delay, as I said that before. But anyway, I'll be around the rest of the day. So if anyone has any question or want to comment something, you're more than welcome. Thank you very much.